Hello, AP Chem students, and welcome to Topic 5.2, Introduction to Rate Law. So the learning objective for today is 5.2.a, represent experimental data with a consistent rate law expression. So let's first start off by talking about what a rate law is. So before we get into that, please remember that all chemical reactions are reversible to some extent. This impacts the rate of a reaction. So to remove the impact of the reverse reaction, the initial rate of reaction is studied, which is the instantaneous rate at the very beginning of a reaction. Because when you first start the reaction and you have not accumulated any products yet, you cannot have the reaction going in reverse because there's no products that can act as reactants in the opposite direction. So that's what allows us to remove this impact of the reverse reaction in studying kinetics. So this allows us to write the rate law, which shows the relationship between the reaction rate and the concentration of the reactants. So for the reaction AA plus BB yields CC plus DD, the rate is equal to a rate constant K. You notice that we denote this with a lowercase k. The concentration of A to some power M times the concentration of B to some power N. So in this situation, K is rate constant. That's the concentration of A and the concentration of B. And M and N are exponents that must be determined experimentally. You need to determine this by studies. You cannot get it just from the stoichiometry of the reaction. Okay. There is one exception to that. If we are talking about elementary steps, then you can look at the coefficient, but we're not going to do that until a little bit later in Unit 5. So the order of reaction comes from the values of the exponents. Each exponent gives the order of the reaction with respect to that reactant. And then the value of all the exponents added together gives the overall order of the reaction. So when you represent order, first of all, zero order does not show the reactant in the rate law, right? Because it's raised to the power of 0, and anything raised to the power of 0 is 1, and so in the rate law, it just kind of looks like it disappears. First order has an unwritten exponent, as is typical with ones in chemistry. We tend to not write the number 1. And then second order has an exponent of 2. Third order is very rare, but it would have an exponent of 3. So essentially what second order and third order means is that you need like 2 of those molecules, or in third order, 3 of those molecules to come together for the reaction to occur. And so that's why third order is so unusual, because that would be highly improbable that that would occur. So for example, in the reaction 2NO plus 2H2 yields 2N2 plus 2H2O, the rate law was determined experimentally to be rate is equal to K times the concentration of NO squared, and then times the concentration of H2. So this reaction is second order with respect to NO, and it is first order with respect to H2. Again, there is no exponent written for that because it's an unwritten one. And then it's third order overall because we add 2 plus 1, and that equals 3. So the rate constant is dependent on 3 factors. It is dependent on the particular reaction, it's dependent on the temperature, and it's dependent on the presence of a catalyst. So the units for K are equal to liters to the power of order minus 1 over moles to the power of order minus 1, and then times seconds. And so now this is if your time units are seconds. If your time units are minutes, then it would be minutes on the bottom. If your time units are hours, it would be hours on the bottom. Normally, we often see seconds. That's usually the speed at which we're examining things in the lab, but it doesn't have to be seconds. So notice that the units of K depend on the overall order of the reaction, right? This is overall order. And I also want to point out that liters over moles is molarity inverted, right? So that's where this is coming from. This is coming from the concentration. So for your total reaction order, your units of K would be molarity, moles over liters, and then that seconds would be on the bottom. So moles over liter seconds. First order, it would be 1 over seconds. Second order, it would invert. So you'd have liters over moles times seconds. And then third order would be liter squared over moles squared times second. Again, if your time unit is seconds. So we use a process called the method of initial rates. So remember that the exponents in the rate law must be determined by experiment, and one way of doing this is called the method of initial rates. In this method, you carry out several experiments using different initial concentrations, and then you measure the rate for each. The results are then compared, showing how the rate is dependent on the concentration. By comparing several trials, the exponent for each reactant can be found. So let's examine this with that data. So trials to be compared are chosen based on their concentration. So for two trials in which the concentration is the same, the two concentrations will cancel out in the ratio and that reactant can be ignored. Therefore, to determine the order with respect to each reactant, choose to compare two trials for which the concentrations of all the other reactants do not change, if you can. So let me show you what this looks like. So if we have reaction A plus 2B yields C, okay, here's our experimental data. Remember that the rate law will have the form of rate is equal to K. Very important, it is not a rate law without a rate constant. So K times the concentration of A to some power M times the concentration of B to some power N. So to determine the exponent for A, we're going to use, so we're looking at A, and so we want this to change and we want B to stay the same. So we have three trials in which B stays the same. So you're either going to choose trials 2 and 3, or you're going to choose trials 3 and 4, or actually you could do trials 2 and 4 if you wanted to. Personally, I like to choose two trials that are right next to each other. It makes the reading the data a little bit easier. Okay, so let's just randomly pick trials 2 and 3. And so you'll see here that what we've got is we've got A for trial 3 over A for trial 2 to the power of M is equal to your rate of trial 3 over your rate of trial 2, okay, to some power as well. So when you do this, what we do is we see that you end up with this ratio is 2. So the rate changes by a factor of 2 and the concentration changes by a factor of 2, which means that your order here is 1. So if you double the concentration and you see that the rate also doubles, then it is first order. Okay, so then to determine the exponent for B, we're going to choose two trials that don't change for A, and so that's trials 1 and 2. We see that there. And so then if we look at the rate of 2 over the rate of 1 is equal to the concentration of 2 over 1, that change, we can see that as the concentration doubles, our rate also doubles. And so B is also going to be first order. And so then when we write our rate law, we can see that rate is equal to K times the concentration of A times the concentration of B, and that is all. So then our evidence for this is that as A doubles while B is held the same, the rate doubles, and then as the B doubles while A is held the same, the rate also doubles. So then that tells us because both A and B cause the rate to double when they double, the order with respect to each is first order, giving the rate law shown above. Okay, if you're asked in a question, and it's not asked in this question, but if you are, after determining the rate law, you can choose one trial, any trial, it doesn't matter which one, pick a trial, plug in the values for rate and the two concentrations, use your newly discovered exponents, and then you can calculate your value of K. And remember that K will not change as long as your temperature changes and your reaction stays the same, okay? So what should I be able to do with this? Because that is it. That's it for this whole topic. You need to know the meaning of 0 first and second order. You need to be able to write a rate law for a reaction by the method of initial rates, by comparing data from multiple trials to determine the order of each reactant in the rate law. You need to be able to determine the overall rate order for the reaction, and you need to be able to calculate the rate constant K and express it with correct units. And then finally discuss the factors that impact the value of K. And that is it for topic 5.2, and I'll see you soon for topic 5.3.